Hey guys, you've been a little testy lately, so I thought I'd give you a little test. I made this review video to help you out with what you need to know, all of the mathy of the transformations.
We have translations, and we talked about translation vectors. We have reflections, and we talked about reflections over the axes on the coordinate plane. We also talked about reflections over those diagonal lines, y equals x and y equals opposite x. We talked about rotations, right? 90 degrees, 180 degrees, 270 degrees on a coordinate plane. And then finally, we covered a non-rigid transformation, dilations. We had a very simple rule for it to do the mathy as long as the center of the dilation was the origin on the coordinate plane. I suggest that you practice so that you may elevate yourself and elevate your grade on the upcoming test. And then maybe we won't be quite so
testy.
Vectors, right? Using vectors for a translation. Remember that vectors have both magnitude and direction.
Magnitude and direction.
When we have an object and we want to translate it, we can do horizontal translations, we can do vertical translations, but when we do a diagonal translation, it's easier to represent it as a vector. My vector goes between each of my vertices. Call this A and A prime, B and B prime, C and C prime, for example. If this vector was called V, for example, vector V, we could break that vector down into its components. Its components are a horizontal and a vertical. Right? Notice we just make a right triangle with it. So we have the horizontal component and the vertical component, right? In this case, it's my horizontal component is 8 units to the right, and my vertical component is 6 units down. And we write that as 8, -6, right? And we call this
vector component form.
This triangle is moving 8 to the right and 6 down. It could just follow the vectors in a diagonal path. We also calculated the magnitude of the vector, which is, we simply use Pythagorean theorem, right? Then that means that the magnitude of this vector is 10 units. Let's do a sample problem. All right, so here we have a problem with a translation vector. So we're going to translate the triangle DEF given here using the vector V, and we're given the component form of -5 and -9.
This is my delta X, and this is my delta Y.
So that means we're going to go 5 to the left, and we're going to go 9 down. So let's start with D. We're going to go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and that's going to be my D prime. With E, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's going to be my E prime. And finally with F, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that gives me my F prime. My pre-image. And this is my image, right? The image being your final destination. I can also draw my vector like this, right? And this is vector V. If I was additionally asked to find the magnitude of the vector, I could do that simply by using Pythagorean theorem, and I would take the square root of -5 squared plus -9 squared, square root of 106 units. And we'll leave it just like that. That's the length of the vector. Right, and that's how we use vectors and vector components to show a translation on the coordinate plane. All right, the next transformation maths we looked at were reflections on the coordinate plane. And we had rules for 4 different types of reflections, right? So let's just visualize them first. All right, so the first reflection was over the y-axis. And there was some confusion with that because if I reflect over the y-axis, I'm doing a horizontal reflection. I'm going from left to right or right to left. And that means what's going to change is my X values. Okay, so keep that in mind. When I do a vertical translation, it's over the X axis, right? So if I reflect over the X axis, that is a vertical reflection. It's up and down. And so up and down means I'm going to be changing the Y values.
Quick review, Y axis, you're changing the X values. X axis, you're changing the Y values.
All right. We also looked at a couple diagonal reflections. one diagonal reflection was over the line y equals x, right? And the line y equals x is the line with a slope of 1 that passes through the origin. The thing to notice here is that if I call this side of my right triangle my x value, down here my x becomes my y value, right? This is left and right, and it becomes up and down. Whereas the up and down, my y value, becomes my left and right value, or my x value, right? So what happens here is what we call the inverse, right? Our x becomes our y, and our y becomes our x. We also looked at the diagonal y equals opposite x, right? And if we do y equals opposite x, then we see that x becomes our y, and our y becomes our x. But there's a little difference with the signs, right? The signs also change. Okay, so we learned 4 reflection rules on the coordinate plane, right? So for reflection over the y-axis, remember that's a horizontal reflection, our xy maps to opposite x, y, right? Remember, it's the y-axis, but what's changing is our x value. The reflection over the x-axis, our xy maps to x opposite y, right? So with the x-axis, because it's a vertical reflection, it's our y value that changes sign. When we reflect over our y equals x, remember that's the one where the values switch, right? We call that an inverse. So xy maps to yx, right? And then the reflection over y equals opposite x, that not only do x and y switch places, but they also switch signs, right? So our rule for reflection over y equals opposite x is xy maps to opposite y, opposite x. All right, so let's try a problem where we're going to reflect triangle PQR over the line y equals x. So the first thing we want to do is to remember our rule, to take xy and map that to yx. Let's go ahead and take our points and apply the rule. So P is at -6, 3, and if we map that to our, what we'll call P prime, right, the corresponding point on our image, that's going to just be these two numbers switched around. So it becomes 3, -6. Notice I keep the negative. I don't change the sign. So for Q prime, I'm going to have 6, -3. And then for R prime, I'm going to have 1, -2. We can plot these points. And one other thing we should do is we should draw the line y equals x. So probably the easiest way to do that is to just pick 2 values where your y and your x are the same. For example, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? And then I can go ahead and take my straight edge and going through the origin, go through that point, right? And then that's my line, y equals x, also called the identity line. Though remember that the orientation on reflection changes. So PQR is, I read that in a clockwise direction, but P prime, Q prime, R prime, I read in a counterclockwise direction. All right, and the next transformations were right rotations on the coordinate plane, okay? Here it's important to point out that our center is at the origin always for these rotations. So I'm gonna use this right triangle to demonstrate what happens when I do a rotation. Okay, so notice if I rotate at the center and I do 90 degrees clockwise, right? A clock goes in this direction. So if I just turn it 90 degrees clockwise, notice what happens. If we think of the shorter side of the right triangle as being our x value and the longer side as being our y value, just like the reflection we did over the line y equals x, our x becomes vertical and our y becomes horizontal. In other words, our x and our y change places. What's different with this one is that signs also change. So for example, notice that this x is negative because it's going to the left. But when I turn 90 degrees clockwise, that x goes up, it becomes positive. So in a clockwise rotation, our x changes sign. Whereas notice the y is going up, it's positive. And now the y is going right, it's still positive. So the y doesn't change. So that leads to our first rule for right rotations on the coordinate plane, or a 90-degree clockwise rotation around the origin is going to give us the rule that xy maps to y opposite x. What happens if we rotate counterclockwise? Well, again, our y and our x trade places, but in this case, our y is down, negative, and it becomes right, which is positive. So it's our y this time that changes its sign, whereas the x, which is positive, goes up and remains positive. So when we rotate 90 degrees in a counterclockwise direction, we get the following rule. We get that our xy maps to opposite y, x. Okay, the important thing to see though is that both of them, in both of the rotations, whether it's clockwise or counterclockwise, we switch our x and y value. The third rule that we have is for a 180-degree rotation. Now, something happens when you rotate 180 degrees. If I go clockwise or if I go counterclockwise, I end up in the same position, right? So we say that clockwise rotation of 180 degrees and a counterclockwise rotation of 180 degrees are equivalent. So what's special about a 180-degree rotation is that the x and the y change places and change back. So they end up right back where they started. So notice in my rule, xy maps to opposite x, opposite y. Again, this is different because the x is in the first position again. They don't switch. Why do the signs change? X goes from negative to positive, and the y goes from positive to negative. Very simple rule. You want to memorize this one, right? And then the other thing we talked about was 270-degree rotations. I do a 270-degree clockwise rotation. That's 90, 90, and 90. It gets me right to here. Well, I could have, rather than gone 270 degrees this way, I could have just gone 90 degrees in a counterclockwise rotation. So if you see a 270-degree rotation, do the equivalent rotation, which is just 90 degrees in the opposite direction. All right, so let's look at this problem. We have trapezoid trap, and we want to rotate trap 90 degrees clockwise around the origin, right? So remember, clockwise is in the direction of a clock. And I'm going to first show you how to do it with the rule, and then I'm going to show you how you can do it without explicitly using the rule. X, y is going to map to y opposite x. First comes our y, so in this case, I put the 4 first, and then I put the opposite of x. Well, my x is -7, so the opposite is +7, right? Okay, so for r prime, first I put my y, which is again 4, and then I put the opposite of my x, which is the opposite of -5 or 5. For a prime, my y is 1, and the opposite of my x is 2. And finally, for p prime, my y is 1, and my opposite x is +8. Okay, now that I've gotten my points using the rule, I can plot those points. So and there's our rotation. Now, for my honors students, I want you to show that rotation by going from the center of rotation to one of the points. I'm just going to pick A because it's nice and close, and A prime, right? And then I'm going to show that this is rotating clockwise 90 degrees, right? And I could also measure that with my protractor just to check it. Okay, so there's my 90-degree clockwise rotation about the origin. Now, let me show you, if you don't want to do all the mathy, how can I do this rotation simply by counting? I always start at the origin and I say, where is my, let's start with T. So where is my T? I go 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4. Now switch that around, 4 and 7. So I go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, and I get my T prime. How do I know it's in the first quadrant? Well, 90 degrees clockwise, it's always going to be in the quadrant before it, right? This is 1, 2, 3, 4. It's always going to be the quadrant prior to the one you're in. So let's do point R. 1, 2, 3, 4, 5. 1, 2, 3, 4. So I go 1, 2, 3, 4, 1, 2, 3, 4, 5, right? Just switch the numbers around. For A, it's 1, 2, and then 1. So I go 1, and then 1, 2. For P, 1, 2, 3, 4, 5, 6, 7, 8, and then 1. So I'm going to go 1, and then 1, 2, 3, 4, 5, 6, 7, 8. Right? If you can plot those points without using the rule, that's perfectly fine. If you use the rule, that's okay as well. One last thing. What if I wanted to change this to a 90 degrees counterclockwise rotation? Where would trap end up? It would end up down here in the third quadrant. So I could plot that really quickly, right? Since T is over 7 up 4, I'm going to go over 4 and down 7. 1, 2, 3, 4, 5, 6, 7. And that will be my T.
And then my R is going to be over 5 and 4. So I go 4 and 1, 2, 3, 4, 5. Right? And then A is at -2, 1. So I go 1 and 2. And then P is at negative 8, 1, so I go 1 and 8, right?
And then you can see same size, same shape, same orientation. All right, hope that helped. All right, and for our final transformation rule, we're going to look at dilations. Dilations are not rigid transformations, but the image is similar to the pre-image, right? It's not congruent, but it's similar. So it's such a simple rule that I'm just going to start off by discussing the rule. The dilation rule, if the center's at the origin, this is very important, right? This only works if the center's at the origin. We can just read this as xy maps to the scale factor times x and the scale factor times y. So you're just multiplying all of your numbers by the same scale factor. Let's look at a problem. So we're going to dilate the pentagon, penta, and we're going to use a scale factor of 2 and a center at the origin. Okay, so I have the points listed here, P, E, N, T, and A. And the mathy is, all we're going to do is multiply all of these coordinates by the number 2. Negative 2 times 2 becomes negative 4. And 3 times 2 becomes 6. Right? 0 times 2 is still 0. 2 times 2 becomes 4. 3 times 2 is 6. 4 times 2 is 8. 5 times 2 is 10. And negative 3 times 2 is negative 6. Negative 4 times negative 2 is negative 8. And negative 2 times 2 is negative 4. All right. All we did was multiply all of our x's, all of our y's by our scale factor of 2. We can go ahead and plot these points now.
And make sure you connect your dots in the order given, right? So P, well, I started at A, but that's okay. I started P, E, E to N prime, and then N prime to T prime, and then T prime goes to A prime, right? And then, of course, the A prime goes back to the T prime.
And we can see that we have a larger figure. In fact, it's 2 times as large. So do the mathy on these ones. If K is less than 1, if it's a fraction less than 1, then you're going to get a shrink, right? Otherwise, you're going to get an expand. Also, watch the scale on your paper to make sure you're going to have room for your figure. You can change the scale to something other than 1 if you need to. All right, so I hope that was helpful.
Learn all of your rules, practice your transformations on the coordinate plane, and I'm sure that you will be successful on the test.
Remember, you study together, but you test alone.
You study together,
but you test alone.